Okay, so today we're talking rejection sampling. We talked about this on Friday, and after the lecture, some students came up to me and they were like, "You used pi half," and I was like, "Oh yeah, I made a mistake." So I've got to let me make some corrections to the lecture, or well, I'll just go over the uniform case again, and then I'm hoping we'll have time to go over the general case. And we'll start with the uniform case. I've got some animations that I worked on this weekend that I hope illustrate how this thing works, and we'll go from there. Okay, so continuing on, we're doing rejection sampling, and this will have a uniform proposal distribution. Okay, and this is something I didn't quite do last time. The PDF is proportional to sine of x. I think last time I just read the PDF is equal to sine of x. That's actually not true. The PDF is proportional to sine of x for x being between 0 and pi. And so when you go from 0 to pi, the PDF will look something like this, okay? Now, I have to say proportional to, because for this thing to be a PDF, the whole thing has to integrate to 1, right? So f of x is actually going to be f of x is equal to some constant, we will call this I'll just constant c times sine of x, all right? And so let me just integrate from 0 to pi of sine of x dx. And this will give me negative cosine of x evaluated from 0 to pi, and this will give me 2, right? So this tells me that the constant that I need is going to be 1/2, okay? So c equals 1/2, and so my PDF f of x is equal to 1/2 sine of x. Okay, so far so good? Okay, so this is going to be the target distribution. This is the distribution from which I want to sample. This is a simple distribution, and so we could easily implement the inverse CDF method, okay? But for our class, we're going to illustrate rejection sampling. And so the idea with rejection sampling, where did my color palette go, is that we are going to have a proposal distribution. In our case, our proposal distribution is the uniform distribution from 0 to pi. Okay, so we have a proposal distribution, g of x, which is the uniform from 0 to pi, which is equal, g of x is thus equal to 1 over pi for 0 less than or equal to x less than or equal to pi, and 0 for elsewhere. That's our uniform proposal distribution. And what this will do is it will sample all values between 0 and pi with equal probability. Okay? But we don't want that. We don't want excuse me, sorry. All right. We don't want values near 0 occurring very frequently. We don't want values near pi occurring very frequently. We want our PDF to follow the, we want our samples to follow what our PDF says, okay? And so what we're going to do is we are going to just use g of x to propose a value between 0 and pi, and then we will use sample another uniform value between 0 and 1 to decide whether or not to accept it. And so what that looks like is we have to modify our g of x by multiplying it by a constant. So this is actually not g of x, but this blue line is m times g of x, so that m times g of x is always greater than or equal to f of x. Okay, so what is the maximum value of f of x? 1/2. That's the highest that f of x will get, because f of x is 1/2 sine of x, right? So the max value, and let me go to the next slide here. So we're going from 0 to pi, and it goes like this, all right? So, so if f of x is equal to 1/2 sine of x, the max value of f of x is equal to 1/2. I'm kind of like doing your homework for you, but that's okay. All right. So the max value of f of x is 1/2. And then, and what is our g of x? Our g of x is equal to the value 1 over pi. Right. So what do I need to multiply g of x by so that it is always greater than f of x? So we want m times g of x to always be greater than f of x for all x. Okay, so what is m? M is going to be pi over 2. Is that okay? And so when I do that, g of x, so m times g of x will be pi over 2 times 1 over pi. M times g of x is just going to be 1/2, and that will satisfy exactly what I need. All right. This is supposed to be tangential. All right. So m times g of x is going to be 1/2 for 0 less than or equal to x less than or equal to pi, and then 0 elsewhere. Okay, and great. So what we do is we propose x by sampling from g of x, okay, or in this case, uniform 0 to pi. Then we generate u, and then we accept x if u is less than or equal to f of x divided by m times g of x. Okay, and reject otherwise. Is that all right? Okay, so I hope my animation works. So what I spent my weekend doing. If we had the extra time, I think I would enjoy covering Okay, so in this diagram, what we see here, this is just the thing working, is it's just cycling very quickly between propose, sample, accept, or propose, sample, reject. Okay, propose, sample, accept, propose, sample, reject. Okay, so the propose is the vertical bar. Here, let me just cycle through this, okay? So first, it's going to propose a value between 0 and pi with equal probability. Here it looks like it proposed a value like 0.9-ish, okay? Then it samples a value u between 0 and 1 vertically, and this is the spot right here, okay? And then, and if this value is below the curve, it will accept the value. If it's above the curve, it will reject the value. And so in this case, it accepts it, and it draws a little blue dot. I don't know if you can see the color here. Maybe here, let me, rejection sampler animation. I think, let me just generate this again. Maybe after the homework is due, I'll, okay, so here it is. Okay, this will go green and red. All right, so let me. Okay, so we're proposing a value. We generate a value between 0 and 1, and then if it's below the line, we'll accept it, and we have a green dot here. Okay, and then it goes, and so in this case, we're going to save this value 0.9-ish. Okay, then we propose another random value. So here we've proposed a value around 1.8. Okay. There's a pretty high chance it's going to be accepted, okay? It has to, and our random value u has to be up here for it to be rejected, okay? So we almost rejected, but this is the value we sample u, and we accept it, okay? Over here, we propose this value. We sampled this value u, and so in this case, it gets rejected, okay? So this value of 0.7-ish or whatever will not appear in our sample. Okay, so we end up having to throw that value away. Here we propose this value. We propose a value like 2.95. Okay, we sample a value of u. It ends up here, so we're going to reject that. We're not going to accept that. Okay, here we propose this value. We sample this value down here, and we accept it. Okay, and so let me just keep playing that. And so this is just kind of how it runs. And you can see it's just proposing values between 0 and pi with equal probability, but whether it accepts or rejects that value depends on how tall the PDF is at that spot, okay? And so what ends up happening is that the resulting sample of accepted values will follow the PDF that we desire. Okay, does this animation kind of make sense and help see what's going on, how this how the thing is working, okay? And so here, let me just kind of show here. So that one I just ran 20 iterations, and this is what ends up happening at the end of the thing is that oh, come on, computer. All right. Okay, I'll just have to live with this. All right, so these are kind of the 20 values it proposed, and I rejected some of them and whatnot, okay? Here, I'm going to turn off the animation, and I'm going to just go ahead and do like a whole bunch of these things. I probably shouldn't show you my code. Makes your homework too. And then, so here we can kind of see this is the resulting histogram of our things, which follows our PDF quite nicely. Okay, I mean, this is just a random sample, so of course it's not going to be perfect, okay? And if we were to just kind of plot this, and this is like all the points, you can see this is what it does. It just proposes values all over the place, and only those that fit under the PDF get accepted. Yes, question?
So how come the max value is 1 instead of 1?
Oh, here I'm plotting it against the ratio PDF of S divided by M times G of S, okay? So basically this ends up being 1/2, so it ends up being the PDF times 2, okay? So here I'm plotting against the ratio. Okay, is that all right? And I did the ratio to kind of illustrate that you're generating a value between 0 and 1. Okay, but I could have left it at 1/2, and then you're generating a value between 0 and 1, but then you're multiplying it times m of g. M times g. Yes, question?
So you sample between g of x, sample from like 0 to pi to get the x value, and then
Yes.
sample again from 0 to 1.
Yes. Every value requires at least 2 samples, probably more. Well, okay. Yeah. You got to do 2 random uniform samples. So you perform from 0 to pi to propose an x, and then whether or not you accept that x depends on another random uniform between 0 and 1. Okay? And so sometimes this means you will propose an x. You might propose an x near 0. That's going to happen with equal probability of proposing a value near pi. You might propose a value, but then when you generate the value between 0 and 1, you end up rejecting it. Okay, so you end up throwing away quite a few samples using rejection sampling, and depending on and we'll talk about this. Depending on what your thing looks like, if the envelope, kind of your proposal distribution, has a severe mismatch between the desired PDF, you're going to be throwing away a lot of samples. Okay. But this is just to kind of give you the idea of rejection sampling. You propose from some other distribution, and then you check, sample another uniform value, and you check the PDF, and you see if you should accept it or not. Okay, and I just kind of I drew a couple more things. So one is the uniform sampling. Here, this is just to kind of show that all values between 0 and pi get sampled with kind of equal probability. So here I'm just showing. When I run the uniform sampler, like pretty much everything between 0 and pi gets sampled kind of with equal probability. Maybe, because it's random, some values might appear more or less frequently than others, okay? And then, okay, so we did this, and all right, we don't need that. All right, and then here, let me just kind of, I want to just look at 2 little slices here. Okay, we're going to look at a slice near 0.2 and a slice near 1.1. Okay, so if here I'm going to just randomly sample 10,000 values, and we're going to just see how many values, I'm going to, within this window between, this is going between 0.2 and 0.22, okay, I'm going to zoom in just on this tiny, tiny, tiny little window, okay? So what appears to be like a steep slope here, we're going to zoom in on this window, and it's going to kind of stretch out, and it'll appear almost like the amount of slope will be quite more flat. Okay, so if I do this, this is now zooming in on kind of the 0.2 to 0.22 here, and this is still that window. And so you can see all these values between 0.2 and 0.22. All of these values are proposed with about equal probability, okay? And here we're going to sample values between 0 and 1, and some of them end up below the PDF, and some of them end up above the PDF, and so I only end up accepting a few of these values. Okay, let's if I go back to this plot, now let's take a look at 1.1. I'll zoom in right here, and so the PDF will be close to the top here. Okay, so the PDF is way up here, and values between 0 and 1 are sampled with equal probability, And in this case, most of these values end up getting accepted, and only a few get rejected. Okay, and so if we go back to the whole thing and just look at those two little slices, this is back on the regular scale. We can see these were those exact points that I sampled and I'm plotting them here, and we can see that we are rejecting a lot of points and accepting only a few. Here, we're rejecting a few points and accepting a lot of them. And so the resulting sample ends up having the correct proportion of points from each of these values. So even though values near 0.2 are sampled with equal probability as values of 1.1, those that get accepted will follow the appropriate PDF. Okay, and then here if I just kind of throw all the points in there, this is the resulting plot with thousands and thousands of points or something. Okay. All right, is this okay? So that is the uniform sampling, and it's kind of, I think, easy to grasp because the idea of having an even thing works out. But we might want to have we might have a PDF that will not work for uniform sampling. Okay. So let's talk about the general case. Okay, so this is going to be rejection sampling. Or I guess before I go on to the general case for rejection sampling, are there any questions on the uniform case using the uniform proposal? Okay, rejection sampling, general case. Okay, so the general case, you will have a proposal distribution that's not necessarily uniform. Now, why would we want something like this? Well, in some cases, you might have a PDF that goes from negative infinity to positive infinity. Okay, so what if your PDF might PDF might go to infinity, all right? And if that's the case, you can't have a uniform distribution that goes that's infinite, right? Because then your f of x would be 1 over infinity, okay? You can't, that's not possible, right? So we cannot have a uniform distribution from minus infinity to infinity, or even 0 to infinity. Okay, that's not possible because f of x would then be 1 over infinity or something. Okay, this doesn't work. So our proposal distribution can no longer be uniform. Our proposal distribution needs to go to infinity as well. We'll also need to extend to infinity. So the idea is still the same, okay? The big idea remains the same, it's just, it looks a little bit different, okay? Okay, so you have a target, we have target PDF, which is going to be our f of x. And we have proposal proposal PDF, which we will call g of x. Okay. The idea is it's easy to sample from g of x, whereas it's hard to sample from f of x directly. Okay. Hard to sample from directly. And this one will be easy to sample from. Okay. And both will have the same domain. Or at least, the domain of g of x will be wider than the domain of f of x. So that's where we start. Then the algorithm works the same way. Okay, you propose x from g of x. Okay, and then we have a constant m, so that m times g of x is greater than or equal to f of x for all x. Okay. Then we generate u from 0 to 1, and then we accept x if u is less than or equal to f of x divided by m times g of x. So this is exactly the same as the uniform case. Okay? The only thing that's different is that in the uniform case, the g of x is a constant, right? In the uniform case, your proposal PDF is just a constant. If you're proposing values from 0 to pi with equal probability, then your g of x is just the constant 1 over pi. Okay? If you're proposing values on the interval 0 to 2, then your proposal PDF g of x is just 1/2. Okay? Not that big of a deal. Here, it's the exact same thing, except your g of x is not just a constant, it's a function of x. That's the only thing that's different. And so now, finding this m gets just a tiny bit trickier. Okay? Finding the m gets just a tiny bit trickier. But the general idea remains exactly the same. So, so the example I'm going to do is going to be, we're going to try to get values from the normal distribution, except this we're going to call the folded normal distribution. Okay, so our target PDF is going to be the folded normal distribution. Okay, what is the folded normal distribution? Okay, so here's the normal. Okay, well that's supposed to be the normal. The folded normal is just the positive half, okay? This is the folded normal, 0 and so on, okay? And so this thing, it's basically the same as the normal distribution, except it's only for positive values of x, and thus it's going to be twice as tall as the regular normal, so that it still integrates to 1. Does that make sense? Okay, so the normal, okay, so this normal has PDF f of z, which is going to be 1 over root 2 pi e to the negative z squared over 2. All right, and the folded normal we will say is f of x, and this is just going to be twice as tall because it covers half the spaces. So this is for z on negative infinity to infinity. Over here, it's going to be just twice as tall, 1 over root 2 pi e to the negative x squared over 2 for x on the interval 0 to positive infinity only. Okay. Does that make sense? Everybody's good with that? I want to make sure I'm not losing anybody yet. Okay, and so even though we're only looking at the positive side, I still can't use the uniform distribution because the uniform distribution would have to go from 0 to infinity, and I would have an f of x, or a g of x of 1 over infinity, and that's not going to work. Okay, so what we're going to have is we will have the proposal distribution will be the exponential distribution. Exponential distribution with lambda equal to 1. All right, what does the exponential distribution look like in that case? Okay, so g of x, our PDF of the exponential distribution, is going to be is lambda e to the negative lambda x, right? And so this just becomes e to the negative x. So that's g of x, right? And this thing looks like, what does this look like? It's hard to draw, okay? All right. Oh, I think you guys know what I'm trying to draw. So this is g of x, right? Here we have f of x, and here we have g of x. Is that okay? So let me just kind of plot these two things. Okay, so that's the exponential distribution. And this is, so in blue we have the exponential distribution, and in black we have the normal PDF, okay? Now, I can't do this because right now my exponential distribution dips below the normal PDF, okay? And that's going to be a problem because if I'm proposing values and we're going to accept based on the ratio between this and this, you know, we're not going to be proposing enough values here and whatnot. So what I have to do is I have to multiply the exponential PDF by some constant m so that the exponential PDF ends up being always taller than the normal PDF, okay? So what I want would be something that looks like this. So here I just multiplied the exponential PDF by a constant. So if we just compare, so here is the normal in black and the exponential in blue. All I'm doing is I'm just multiplying the exponential by some constant so that it is always taller than the normal, okay? So how do we find that? How do we find the constant with which to multiply? This requires a little bit of work, okay? So, so again, our f of x, our target PDF, is 2 times 1 over root 2 pi times e to the negative x squared over 2. And our g of x is equal to e to the negative x, okay? So what we need is we need to find m, okay? M needs to be greater than, or, you know, just, well, we're going to find the maximum value between the ratio of f of x divided by g of x, okay? So we're going to see basically where f of x is the largest in comparison to g of x, okay? So basically on our graph, it's basically we need to find where f of x is the tallest versus g of x, which is probably going to be like right here versus right here, okay, or something, where the vertical distance is the greatest, somewhere around here, okay? We need to find this thing and find out the ratio here, and then we're just going to multiply it, multiply the blue by that kind of ratio so that it brings it up to equal, okay? So we, basically m needs to be greater than or equal to this, so we just want to find the maximum value of 2 times 1 over root 2 pi of e to the negative x squared over 2 divided by e to the negative x, okay? Which, so find the, basically maximize x. So this becomes 2 times 1 over root 2 pi times e to the negative x squared over 2 minus x. Okay, so the maximum of this will occur where? At the minimum of x squared over 2 minus x, right? Because it's raised to the negative x. So if we can minimize this, this will be the maximum value of this whole thing, and then we can just plug in the x there, right? So where is this thing minimized? X squared over 2 minus x. So we would do x squared over 2 minus x. We're going to take the derivative of this. Whoops, sorry, that's not on your screen. So we do d dx x squared over 2 minus x. And we get x minus 1. So this happens at x equals to 1 will be our minimum, okay? And then so what we find is that m needs to be greater than or equal to 2 times 1 over root 2 pi e to the negative 1/2 minus 1, okay? And all right, so you figure this out and you get something around 1.32-ish, okay? With R, it's easy to do this, okay? All right, is this okay, the math that I did here? So we're trying to find the m to multiply our g of x by, so that m times g of x is always greater than or equal to f of x. And that's going to happen where f of x is divided by g of x. We want to maximize that value. Okay, and then so actually, in R, it's quite easy because all you have to do is you just say, the PDF divided by g of s, maximize that thing, avoid any unknown values, and when you do that, here I get 1.315 or whatever. But anyway, so when I plot this and I multiply it, this is what I get. Okay. Okay, and then so this is going to work the same. We are going to propose values according to the blue, the exponential distribution. Okay, and we can just use inverse CDF. That's very easy for the exponential distribution. It's just negative times the log of some random value u. Okay, and then so let me just show you the exponential sampling. So this is to show, this is just when you sample from the exponential distribution, what we will see is that values over here are sampled much more frequently. Okay, that's what we're seeing over here. And as the PDF of the exponential distribution drops off, we see that values out here get sampled less and less frequently, right? So that's why this area ends up much darker, because these values are getting sampled very frequently, and as we go this way, it gets there's fewer and fewer values out here being sampled. Okay, so that's the exponential sampling part. Here, I'm going to close this. And oops, what's going on here? And now we will do the kind of the same thing here. I have the video running a lot faster, but you know, we propose a value from the exponential distribution, so that's going to favor values on this side over this side, which is going to be a good property. And then we draw a random value u. Okay, and so now actually this is the wrong word here. The random value u is multiplied by our exponential, and so 100%, 1 would represent a value all the way at the top of the this line segment, and down here would be 0, and somewhere halfway in between would be around 0.5. So in this case, we sample that, and we would accept it. Okay, here another random value is sampled. Again, it's favoring values near 0. And we propose a value, and in this case we sampled a value close to 1, so this ends up ending up over there, and so we are going to reject it because it's above the line. Over here I propose a value near 1, okay, and in this case, like, the entire thing is right below the line, so whatever I'm going to sample is almost for sure going to be accepted, okay. And over here, a value near 0 is, you know, going to be sampled quite frequently from the exponential distribution. But then we have to see whether to accept that or not. We sampled a value down here, and so we will accept it. Okay, and we just continue this, and so I'll just let this run. And what we will see is that, you know, values out here don't get proposed very often. And when they do, they may or may not, you know, they'll probably get rejected, okay? But you'll see that the sampler, because we're sampling from the exponential distribution, will favor values near 0 a lot more frequently, okay? Does that kind of make sense? Yes, question?
So that doesn't cause a problem, though, that we're only sampling mostly from, or not only, but that...
No, so because... yeah, it's not a problem because we handle it by using the uniform distribution to decide whether or not to accept or reject that value, okay? And so even though we are sampling values from over here quite a bit, okay, because we are comparing that to the normal PDF, we say, oh, you know what? We don't want to accept every single one of these, okay? And we're going to reject, you know, quite a few. When they're tangential, we're going to accept pretty much every single one of these values. And then down over here, we're going to reject quite a few. And this will work because both PDFs extend out to infinity. You know, they're asymptotic and they both approach 0 as we approach infinity, but the normal one actually just drops off a lot faster. Okay? And so in that case, I think I did like 20 or something. So let me just show you. Oops. All right. Let me just. Or I did 50 values. Okay. Okay. So these are kind of the 50 values that were proposed, and so you can see we don't propose values out here very often, and when we do, these values are rejected, and so on. And so if we look at the histogram of sampled values, this is the exponential, but then when we, this doesn't look very great. But for the ones that are accepted, here, let me just kind of fast forward and just say, what if I did 10,000 points? Okay, so you can see the values that get proposed follow the exponential. The values that get accepted follow the folded normal. Okay, and so if I create a histogram of the ones that we've accepted, this follows the normal PDF quite well. Whereas if I look at the ones that are proposed, this follows the exponential. Okay, so the proposed values follow the exponential, but because we don't accept every single one of them, the accepted values follow the normal, okay, or at least half the normal. Now, how do we go from the folded normal? This is just mostly for your homework. Because the normal distribution is symmetric, I can basically take any of these values and then flip a coin with probability 0.5 to decide whether this should be a positive value or a negative value. And if we do that, then we will no longer have the folded normal, but we will just have the regular old normal distribution. Okay, and so this is basically what you'll be doing in your homework. You obviously don't have to draw the animations out and things like that, but well, I hope the animations were helpful in illustrating how the samplers are working. Okay, so that's rejection sampling. Okay, and with that, we'll see you guys on Wednesday.